Okay, what we're here looking at today is a way to graph in the world of physics, and really any of the sciences or anything you're doing. And it's just a quick little overview as we get into it, and we'll show you some stuff for Google Sheets or Microsoft Excel if you're using it. So, first thing we got to realize is if we have an XY axis set up here, our X axis will be the independent variable, okay? It is the independent. The reason why we call this the independent variable is because our y-axis is the dependent variable. And the way we can think about it in a few different examples is imagine that we are sitting on a lake or a river. There's the blue water. And we've got a boat, right? Here, let's make a green boat. This boat is sitting at some depth in the water, and it's dependent on how much you fill the boat up with stuff. So if this is like a barge going down the rivers of Pittsburgh, we'd fill it up with something very Western PA like coal in this time of 2020. And as we put more coal into it, the barge is going to sink lower in the water. And I think just a few years ago, a few barges actually got loose off of their boat and ran down the river and sunk, which was kind of the news thing of the day. We can just keep putting coal into these barges as much as we want. We could shovel it in, we could shovel it out. It is independent. We can do whatever we want with it. The depth that this sinks, though, is entirely dependent on how much coal we put in. If we put more coal in, then it will sink further. If we take the coal out, it'll rise back up. The barge isn't just going to magically go down and up unless we do something to it. So that depth is dependent on our independent variable, which is like the weight of the coal we put in there, okay? So that's how we can think about the independent and dependent variables. And from your math classes, you know that this down here is our x-axis, and up here vertically is our y-axis. And this traditionally, we call this the origin at point 0. Although we can do some stuff to kind of change that if we wanted to. For the most part, we're going to leave it as the origin. Okay. The real big thing to take away here is that x-axis is the independent variable. The y-axis is the dependent variable. Now, what we used to have to do is we used to have to pull out some graph paper, bring out a straight edge, and have to very carefully, and I remember doing this in school with my my 9th grade general science teacher, my earth sci teacher, Mr. Lib. We would sit there and we would make sure that our graph was carefully ticked off, and it would take up exactly 80% of the graphing area, and we would make sure that each of these were properly scaled and divided appropriately, so our graph wasn't too small and it wasn't too big, but it was like just right. And we'd use a nice straight edge so that my lines weren't curved, and we'd be like, oh, look, this is a very nice, beautiful line, and there's an arrow at the end of it to designate it could go on, right? We had to do this all by hand. And now we're in the 21st century, so we hit Alt-Tab on our computer, and we run over to Google Sheets or Microsoft Excel, because it is so much easier to do this and so much faster. When we're using Google Sheets right here, but Microsoft Excel works nearly identical, so whatever you have fun with it. What we've done is I've listed some barge data here. So what I have on the left is the weight of the coal we're adding to the barge in tons, in metric tons, and it goes down this column here, okay? The depth at which the barge is sinking goes right here, and it goes down this column. Now, a few things to recognize. Because my x-axis is my independent variable, the way Google Sheets and Microsoft Excel always looks at data is it sets it up as ordered pairs, x, comma, y. So the x is always left of the y value to the right. Furthermore, when we're using something like Google Sheets, Microsoft Excel, note how I have labeled the weight and the depth in their own row right here. They're in row 1, 2, 3, 4, they're sitting, okay? I do not write 18 centimeters. I do not write 21.5 centimeters. See how when I do that, it shifts it to the left? The computer doesn't actually think this is a number anymore. It thinks it's some combination of letters put together. It doesn't know what it is. So what we do is we just place the numbers here, and in a little parentheses next to our label, we put the units. Metric tons, centimeters, inches, miles, seconds, whatever it is. Don't put them down here by the numbers. Leave the numbers alone. Set those units up in the actual labeling. What we can do now to create our graph is by clicking and dragging through the labels and then down through all of our data, we'll highlight it. And then we've got two options here. One is normally there is a file insert somewhere up here where we could insert our graph or our chart, but we're also looking for a tiny little kind of histogram or a bar chart shape. And if I hover over it and I just let it sit there, it'll say insert chart. And if I click that, it'll try to generate something for me. Now, this looks like a pretty decent chart here, but it's not actually what we want. If we look into our editor over here, and here, let's move the virtual 226 over a little bit. If we look into our editor here, the chart editor, we'll see that in the setup that this is a line chart, and we don't actually want a line chart. A line chart is actually just playing connect the dots, which in the world of sciences is a bad thing. What we want to use is a scatter chart. That is what we want. We want a scatter chart, scatter plot. Just as a side note, see how there's these pie graphs here, these pie charts? Those are the worst charts on existence. Never, ever, ever for anything use a pie chart. The human eye does a bad job of understanding what area is, and for the donut shape, it's even worse. Plus, this is a 3D pie chart here. What do you need a third dimension for? You're not plotting 3 different variables. It's ambiguous. It's very confusing. It's bad charting. So we use a scatter chart here, okay? And now we see dots represent all of our pieces of data. And if we want, we could double click on something like the depth, centimeter versus weight, tons, and we could rename this with a proper title, something to kind of describe this graph. So we could say it's like the effect of weight on barge depth. Okay, so a more descriptive title there. Now, while we kind of can see what's going on here, maybe we want some information on what's happening in between the dots, or maybe after the chart ends. And how can we get that information? Well, to do this, we need to fit our data. And the way we could do it is in these little 3 dots, these 3 vertical dots, known as a kebab, we could go in here and edit the chart, bring up our chart editor again. And if we go into customize, it'll bring up more options for us. Well, if we want to get a line of best fit, we'll go into the series option and we'll scroll down until we hit trend line. When we hit trend line, the default in Google Sheets is to plot in a linear trend line here, okay? And if we wanted to, we could change the line color. Let's make it red. But this is a linear graph. And if we think back to our mathematics, a linear graph represents y equals mx plus b. So what we're thinking about whenever we have this linear graph here with a y equals mx plus b is that, here's our y equals mx plus b. This b is what we refer to as the y-intercept. It's physically where, if we look at this line right here, it's physically where we're intersecting the y-axis. Whereas this m value, that is our slope. And if you recall from your math courses, your m, your slope, sometimes they call that rise over run. We can calculate it by saying y2 minus y1 over x2 minus x1, where points on the graph have ordered pairs x1, y1, and a second ordered pair farther away, x2, y2. Now, we used to have to do this by hand, setting up this line of best fit, in which case, if you are doing this by hand, if you're on a desert somewhere and you don't have anything, or technology is lost in the year 3030 and you don't have this video, but you remember it, when you're doing it by hand, it's kind of like an art form. You just do your best. Get something that looks appropriate to fit the data and go with it. Some teachers will say like, oh, have the same number of dots above and below the line, but that's not like a very, good thing to say, so to speak, because as I'll show you just real quick here, it's very easy to make a very stupid line of best fit by following that rule. So imagine real quick we just have here's some data points here, right? Maybe you're thinking, oh, the line is best fit should look maybe something like that. I have 2 above and 2 below. That's good. But technically, that also follows the 2 above, 2 below thing. But that's a terrible line of best fit there, wouldn't you agree? So it's really just a judgment call. Just make your best judgment call, whether you pick the blue line or you pick, the orange line and kind of go more like this. Like, at some point you have to make a decision. You're doing it by hand, whatever. What the computer's doing, though, is it's actually running what's known as a linear regression fit. It's a mathematical term, and it's using math to get the best line. Okay, that is mathematically, on the computer, the best line you can get here. But how do we get the equation for it? Well, if we're not running the y2 minus y1 over x2 minus x1, we're having the computer do it. Well, what we'll do is we'll go down into label, and we'll have it use the equation. Okay, now we see the equation has appeared at the top here. It is the depth, which is the y variable, y, equals, and then we have 0.746, which is our slope, m, x, which is our dependent variable, the weight in tons, plus b, which is our depth right here of about 18. Well, it's exactly 18 as the computer predicted it. Okay, so that's how we can actually get our equation here. Now, in this case, a linear graph works really well. But we can have other graphs in the sciences. We can have exponential graphs, we can have power graphs, we can have sines and cosine graphs for some things. You can have inverse graphs and square root graphs. There's many, many different things that you could generate on different physical properties. What you need to be careful about, though, is when the computer is fitting data, it is just trying to do its best job fitting. So let's just change one little piece of data here. Let's do this. Let's make this a 8. So I took this piece of data, the 4th data input, and I dropped it down here, okay? And we noticed our line shifted a little bit. These values changed. It's down here. Now, if I go into my edit chart, maybe you're looking at this and you're like, okay, well, it kind of looks linear, but like maybe that's a bad data point. Like maybe we should have gotten rid of it. Maybe we took the experiment wrong. Maybe whoever measured this did a bad job. Maybe a wave came and threw the barge out of the water for a second. I don't know. But one way we can see if this is a good fit or not is by hitting this r squared value. This r squared value here, right above my head, is what's known as a goodness of fit. And the closer this value is to 1, the better your fit is. Well, right now it's 0.333. Before, when this value was, I think, 33, it was exactly 1. That's great. But like this, it's 0.333. So you're maybe thinking like, it's not a great fit. Maybe I could fit it with something better. Maybe this graph isn't linear. Maybe it's exponential. Maybe it's logarithmic. Maybe it's power. Maybe it's a moving average. There are additions that you can put on Google Sheets or Microsoft Excel in order to put even more types of graphs. But what I notice for my students is they'll often make this mistake. They'll click polynomial, and look, we immediately became better, 0.645. And we got this kind of weird curve here. If you're looking at this weird curve, what the weird curve is saying is that from about 0 tons to maybe 13 tons, when you put more coal in the barge raises out of the water. Process that for a second. As you put more weight in the barge, it floats more. That makes 0 sense. As you put weight in the barge, it is sinking. It goes down in the water. This curve here is saying that it's doing the exact opposite. You know that's not right. But it's technically a better fit. Should we use it? No, we shouldn't use it. Absolutely not. It's a better fit, but the computer is just trying to run an algorithm to get a line to connect these points. And with polynomials, if you remember your math classes, these are like ax squared plus bx plus c. We can create higher degree polynomials like this. This is a 4th order polynomial here. So that's like ax to the 4th plus bx cubed plus cx squared plus dx plus e, right? And we get this huge equation up here, and it's a perfect fit. And what this represents, according to this squiggly line, is that from here, when we add weight, the barge is sinking, and then once we get past 10 tons, it begins to rise out of the water, and then after about 22 tons, the barge is floating above the water. It's not even in the water anymore, and then we come back and it sinks a lot. Like that doesn't make any physical sense, but it is an option we could pick over here. We could pick a fourth order polynomial or a fourth degree polynomial. The computer has a better time fitting it, but it is a bad fit. Okay, it's a very, very bad fit. It's non-physical. It doesn't make any physical sense. So that's one of the things that if you're just looking for R squared values, and you get some crazy equation, like, that's probably not right. Oftentimes we're going to be, in the physics at least, linear or exponential. Sometimes we'll be log, and those are the fits that we're looking for. 9 times out of 10, okay? So just be careful about that. That R squared value, it's a good indicator of how good your fit is. It is a goodness of fit, but don't purely rely on it, because then you're probably just going to pick a polynomial of high order and say it fit perfectly, but it means nothing at that point in a physical sense of the world, okay? So be very, very careful about that. That's the only kind of weird thing about this. So that's kind of a brief little synopsis on graphing, what we can do here with our graphs. You could go back into the edit chart, go into the customize, and play around with all sorts of stuff. You could fiddle with the axes. You can make them log scales if you wanted to do that at some point in your life. We won't have to do that in this class. If you wanted to change like where the legend is positioned, if you want to put it on the right side or if you want to put it on the left side, there's all sorts of different customization options you could do on this. Just kind of playing around in here. But yeah, that's a quick little Google Sheet graphing, Microsoft Excel graphing, whatever you want to do. Big takeaways: make sure you're graphing this X, Y, that your labels come before your data, and that you're not putting the units under the datas as well, that they are just the numbers. So when you graph this, we just have the numbers here, and we can take a look at everything, and it'll math out properly. Okay? So with that, I am out and away. Adios. Take it easy.